Okay, good morning, everybody, and let me thank the speaker, thank the organizers for this opportunity to present some of the results of our results here. So we'll talk about normal mode analysis of Coulomb particles in trap, irregular trap in particular, and this work is done by my PhD student Vishwarupas, who have moved out, and we benefited a lot with active collaboration with Chandan Dasgupta at IISc. So we will try to get insight on the dynamics of particles in a system which is confined, trapped, and particles are long-range interacting. That's what we would like to look into. We will do the analysis of normal modes, both quenched and instantaneous normal modes. I'll define what they are. In particular, we will focus on the question here in the end, how the low-lying inherent structure, some normal modes, control the long-time dynamic heterogeneity which is actually present in system like this. So I'll explain these words as I go along. So technically what we are doing is, as I said, we'll study, we have been studying the static and dynamics of Coulomb particles in trap for some time. So basically we take a confinement like a parabolic well and throw a bunch of charged particles, interact in Coulomb way. So it could be a circular confinement like this, or it could be something which is disordered or which is irregular. I just squeeze it in some particular way. I have a form of the potential like that, which actually breaks the spatial symmetry, all the spatial symmetry, and which also ensures the chaotic motion of a single particle, single classical particle in such trap. So these two are taken to be the signature of disorder in this problem. We study this in some numerical analysis, and this has been done for some time. We try to understand the melting of a Coulomb crystal in this disordered environment. Found some crossover temperature, the underlying picture of melting. In particular, the dynamics across melting turned out very interesting. So it produces what are called dynamic heterogeneity. I use the word, so just to say, you don't have to look into the picture too much. So this is like the particles, and then sticks are representing the distance by which particle moves in the system at a given temperature. So this is all motions are because of thermal jiggling. So that actually, there will be spatial regions where particles will move more as opposed to some other region where particles won't move. And this is the disordered trap or irregular trap, and this is the circular trap. So these dynamic heterogeneities, these are very standard, they occur in standard glassy systems. And then we try to explain the nature of this dynamic heterogeneity and the glassiness associated with it. And all that have been sort of written up in earlier results from ours. So what we are going to do is, we try to understand different characterization of glassiness. So what we are going to do today is to take do a normal mode analysis, and we'll see how much we can learn from normal mode analysis of these particles inside trap. Okay, so that's what we are going to do now. And so this is what I said. So now what is a normal mode? So normal mode actually addresses dynamic response. It measures how particles in a given configuration, which are performing a collective motion, moves in a system, right? That's the normal mode. So this is the standard thing we learn in our first solid state course, like different modes of motion in a crystal, harmonic oscillator model, etc., etc. So we do exactly that for our problem. So we construct a Hessian matrix which is defined this way. Her Hamiltonian was given earlier, the one in a trap, and also the Coulomb interacting particles. And then we write this down in terms of instantaneous, let's say instantaneous configuration of n particle, like instantaneous configuration, equilibrium configuration, let's say. And then we find out the eigenvalue problem. So the eigenvalues are square of the eigenfrequencies or modes, square of those frequencies. And the eigenvector gives the oscillation pattern of particles in a particular mode. The En eigenvector will give you this thing. So, okay, so now this normal modes can be also looked into what are called quenched normal modes. So where we do exactly similar, we start like exactly similar way. So we take configurations which are evolving, let's say this is a, equilibrium MD simulation, you have different configurations at different time step. From every time step, starting from every time step, you then quench, meaning you try to find the energy minimized configuration by something like a conjugate gradient method and so on and so forth, and you get to what are called inherent structure or quenched configuration. They're just called inherent structure. So remember, many times, many of these equilibrium configuration will get to one single inherent structure, like in this case. So for example, if you had just one single minima, which is very rare in a configuration space, you will just have one inherent structure of the ground state. So in this problem, so now what does this quenched normal mode does? The quenching actually get rid of the small amplitude vibration. So if this was the actual molecular dynamics trajectory of a particle which is moving from here to there, so that in an inherent space, it will look like this. So it has got rid of all the small amplitude vibration. And then the good thing is that here you can talk about from here you can read out the long time dynamics in the system. So to go ahead, what we plot here is what are called the density of states, density of modes essentially, this normal mode. And in a finite system of, let's say this is a case which is for small system with 150 particles in a irregular trap. Henceforth, all the results I'm going to show here are for irregularly confined system, irregular trap, and if required, I'll make comparative statement for circles. So now, if you look at this density of states, so this is very spiky picture, and that is because at a spiky picture, at least for very low temperature, because there are only limited number of inherent structures possible at low temperature, and then with increasing temperature, you smoothen it out a little bit more. So what you can also calculate corresponding to these modes, what is called a participation ratio, so which measures, this is a formula, but essentially what it measures is the fraction of total number of particles which are contributing significantly to a particular mode, motion. These are like polarization vectors, so having large polarization vector for every particle. So that's participation ratio. So now this is participation ratio is very standard to sort of identify what a localized mode and what a delocalized mode. So participation ratio will be large for delocalized mode, and it will be a very small number for localized mode. So we put some cutoff which might look ad hoc at this point of time, that if participation ratio is smaller than some cutoff value, we call them localized mode, and if it is larger than some other value, these numbers are ad hoc for the moment, they're delocalized mode. So if that is so, you can see the participation ratio which is given here as a function of frequency, so it must go from low to somewhat larger value in some region. So those are some numbers which will fall somewhere in between, and again in ad hoc manner for now, we are going to call them quasi-localized mode. We are trying to, so what we'll do for next few slides, we'll try to make it little more quantitative, the existence of this quasi-localized mode. And finally, I'm going to make statement, I'll try to show you that these quasi-localized modes are actually very important to determine the long-term dynamic heterogeneity. So that's the rest of the talk. So now, so because this Hessian matrix is function of supposedly random position of particles in a given configuration, it can be, so the Hessian matrix evaluated at a particular, a particular configuration can be taken as an element of a random matrix ensemble. So with this assertion, what we are going to do, we are going to find out the localization properties, assuming that this system is described by a random matrix ensemble, the Hessian is described by a random matrix ensemble, because then I have an advantage. I can use the concept of random matrix theory to decide which are the modes which are localized and which are delocalized, right? For example, we know that if I take the energy level spacing statistics, so which is defined like this, these are the eigenvalues, so these are neighboring eigenvalues of the Hessian matrix, so that divided by some mean level spacing, so that will follow what is called a Wigner distribution. That's the, if the mode was delocalized. That's the assertion of, that sort comes from random matrix theory. On the other hand, if the mode was localized, then the same distribution will follow, the distribution of the same quantity S will follow a Poisson distribution. So it turns out exactly the same ad hoc numbers that I put before, they actually define very well what a localized mode and what a delocalized mode in terms of this, the statistics of this distribution. In addition, there are modes which are given by this pink line which does not fall either on the Poisson distribution or on the Wigner distribution, and those turns out to be the quasi-localized mode. Now, what I'm saying is it's not just a visual impression of what is fall on which graph, because you can do a statistical analysis, and that is what we have done. So basically whether these numbers which are always a discrete set is actually representing a Wigner distribution or some Poisson distribution or somewhere in between. This is done through some statistical analysis invoking Brody function and so on and so forth. I mean, that details we can discuss later. Okay, so now so we can look at the representative of these plots of this mode. So these are localized mode where particles don't move almost at all. Only small region, very, very small fraction of particles are performing motion, has finite polarization vector magnitude. Quasi-localized modes are the ones where not only that there are many which are not performing any motion, but even those who are performing motion are actually, there is some coherence in the directionality. And the one which is delocalized, that most particles are contributing to the participation ratio, but they are sort of random. So that turns out to be a pretty generic picture. So one can also get an impression of what are the length scales. So if I call something quasi-localized, there are ways to get a length scale, and we have found that number. I'll not get into that. So I will come to the last slide that I wanted to say. Just I'll take a little bit of time. So now what I'm going to say that the fast particle, so if I have a dynamic heterogeneity in the system, so then how does this, I'm going to claim that it is the quasi-localized mode that will determine the dynamic heterogeneity, and it is the following way. I make a list of particles, I is the particle index, which are making, let's say, which are like fast particles, top 20%, fast particle means the ones that have a top 20% displacement over a time interval delta t, time interval starting from t0. Now I take the configuration, the quench normal modes at t0, and then I make a sum like this, where this is sum over all the polarization vector magnitude mod square. However, this sum is a restricted sum, so if I make this sum only over the quasi-localized mode, then it turns out that these two quantities are highly correlated, which are defined this way. So that means whichever has a large value for this thing, the particles which have a large value in this, that will find a large displacement over a long time. So knowing the normal modes at a given time now, I'm able to predict where the dynamic heterogeneity will be there at a larger time, at a large time after, after large delta t. So that turns out to be, so basically what it says that we can explain the structural origin of heterogeneous and slow dynamics, which is often found in supercooled liquid, and people have looked into that. So that works nicely here, and this goes up over some time, attains a peak at the structural relaxation time scale, which can be measured by some other means, and then beyond that it falls. Beyond that it falls, of course. So all it says that the motional signatures are controlled over a long time by a basin, by an inherent structure, which is around which the particle moves, spend little longer time. And then it moves out to a different one, and structural relaxation occurs, go to basin of the other one. So that's the main result, and then I will just flash the conclusion slide here, and I'll be happy to take a question.